Okay, we've been busy using this Waddell Truss as a sort of cause célèbre for defining in our engineering mechanics terms in a formal way these basic concepts of axial stress, average shear stress, and average bearing stress. We calculated values, but so what? Why do they matter? What's going on here? So in the last or fourth part of this item, what we're going to do is compare those to some criterion stresses. And you'll eventually begin to learn how to look these up and find these, but right now I'll just give them to you that for this particular material, that our criterion is that we don't want the tensile stress in the gross part of the member to be more than 36 ksi, we don't want the shear stress to be more than 21 ksi, and we don't want the bearing stress to be more than 18 ksi. Let's take a look and see how we might do this, which is really just a simple ratio. That's all we're going to do. We're going to look at whatever the criterion is and divide by the applied. And so in this case here, we got for the tension, we calculated that we had 13.33 ksi applied. Our criterion was 36. So we have 2.7 times more strength than we absolutely need. Greater than 1 is going to be good. Right? For the shear, we have a criterion stress, this is about the bolt, so of 21 ksi, and the calculated value was 14.14-ish, or 14.1, it's actually 14.147. And so 21 divided by that number is 1.5. Again, that's greater than 1, so from a theoretical standpoint, that's good. Right now, don't look at the bottom one yet. What happens if we have a situation like this and the thing still falls down? Well, wait a minute, what's going on here? Well, this criterion stress that we've used is not necessarily a precise number. It's a little bit of quality control in manufacturing the piece, but there's always some natural variability that's going on. So what happens is that we don't use 1 as our acceptable threshold. Depending on whether it's tension and shear and the kind of material and what causes the tension and shear, well, we might have a factor of safety that's required of at least 1.6, or maybe it's 1.5. So it's not good enough just to be slightly greater than 1, have a little bit more strength than you really need. You need a little bit further edge from the cliff kind of distance there. So think about it as going, if you're at 1, you're right at the edge of the Grand Canyon. Now, some of you might feel highly confident standing at the edge of the Grand Canyon. Some of you are like, I don't know if this cliff is undercut, and I'm a little concerned a wind will come along and push me over the edge, and even though it's a calm day, but I don't anticipate this wind, but what if it happens? So you want to be a little bit further from the edge of the cliff than this. 2.7 is a real good number. 1.5 for shear is starting to get a little close to that additional factor of safety that we like to have beyond 1. But for right now, that theoretically these are both good. The problem here is that with this particular set of loads on the structure, we ended up with bearing on that I-bar that was larger than what the criterion stress was that was given to us. And by about 20%, we're not strong enough. That's absolutely no good at all. It could actually be okay, because again, randomness of what's going on, maybe the actual real I-bar part is going to be stronger than we think it is. So it might actually survive, even though the math says that it won't. But again, that's including the reality of the world, which is there's randomness, there's variability, there's uncertainty about what's going on here. But this, from a design standpoint, we can never accept that particular kind of situation. We can accept these two situations, especially if our threshold values for the minimum factor of safety that we need to have is lower than those two. And we need to have it lower than for all cases. Right? Now, the only other thing you see here is that we have more than one kinds of factors of safety. It depends on what kind of what we call limit state we're comparing against. So we'll get into that more when we get into mechanical properties and the various different ways that materials can behave or really, in essence, fail. and then we'll also talk later on in the semester about buckling and instability types of modes and ways that things can go wrong.